And hi everyone. Thanks for having me, and I hope to have a nice, productive session. This subject is a subject I've been speaking about for a couple of years now, and even though the title stays the same, I do keep updating and adding to it. Um, as the title says, this is a garbage collection talk, and it's focused on education around garbage collection, how garbage collection works, how the various parts and mechanisms work in it. And after about a 90-minute session, you hopefully will be uh, leaving with some better education on the subject. A little background about me and the company I come for before we start. I'm the CTO and one of the co-founders of Azul Systems. I've been working on garbage collection for more than a decade now. And this picture here is some evidence of me working on garbage collection in my kitchen. That's a trash compactor you see there, and it was actually broken, and fragments were coming out the side, and it was pausing and not compacting correctly. So I had to open it up and took a photo up with my trusted garbage collection book at the time. This is way back in 2004, and since then I've been actually building real garbage collectors. There are a couple of peer-reviewed algorithms actually published, and obviously the things in the products at Azul Systems that we do. I have a long history of building all kinds of things, not just garbage collectors, virtual and physical machines, operating systems, firewalls. I helped design CPU instructions and went all the way to nationwide subscriber management systems written in Java across millions of subscribers, and back in a day where we had to build our own application server to do that. So I have about 3 decades worth of mistakes behind me, and some of those could hopefully be taught to others. Um, about Azul, we make scalable virtual machines. That's pretty much what we do. We focused on Java virtual machines, and we've basically had an approach of both focus and pure play, and building whatever it takes to get the job done to make virtual machines behave well. This included over the years many interesting things like 3 successive generations of custom multi-core hardware that we've built. That's that little picture up at the top right here. Those are Vega systems, and they're still running in a lot of large commercial and financial sites today. But about 4 or 5 years ago, in some, we looked at the roadmap for commodity hardware and figured that by 2010, maybe 2011, commodity hardware will be ready to run our things as software as opposed to the custom hardware we needed up to then. We therefore decided to convert our entire stack and focused on Linux x86 commodity hardware as a target. And the product lines we ship today are all focused on that environment. Zing is our flagship product. It's a JVM for Linux x86. It's well known for being very good at low latency, at consistent execution, and at large data set execution, but pretty much across the board. I'll get into it a little bit as we go, but this is not a product pitch, so I'm not going to focus there. It is worth mentioning that we also have another product line called Zulu, which is a regular JVM based on OpenJDK, but in a fully supported enterprise manner. And it's a new product line. We're focusing both on cloud deployments and large enterprises that are not necessarily looking for the high metrics or the low pause capabilities, more at wide-scale deployments. So that's about me and about Azul. Let's go on to the talk itself. Let's start with what the talk is about. It's a GC education talk. It's not a tuning talk. This will not be a talk where I go through every flag in the JVM and explain what it does. It's much more about you understanding how garbage collectors work and what the common terminology is and the various mechanisms and various JVMs are, so that you can then apply that knowledge when you look at the various tuning options and flags that you might have. I'll be going through and defining things as we go, but I'll try and hold back on my pride with our garbage collector, where we absolutely believe it's the best garbage collector on earth, and I'll keep that to the end. In a way, hopefully the terminology and metrics that you learn about here will help you understand that in context. As an agenda, we're going to cover fundamental keys, key mechanisms, and actual fundamentals of GC. We'll define terminology and metrics as we go, and then we'll use those terms to classify the currently available collectors that are on the market. I'll take a detour into discussing the stop the world problem and why it is a big problem, and then discuss the C4 collector, which is what we use in the Zing product, and how it solves the stop the world problem and what solving that problem with Zing or with other products in the future might look like. So that's the high-level agenda for what we're doing. At the start, I like to highlight this point where, since we're not in a room where everybody could raise their hands, I'm going to guess that the vast majority of you fit somewhere in this circle. That's usually what I see in a room of anywhere from 50 people and up. 80% of the people usually are within this circle as far as heap sizes for their applications. And while there are a few people here and there, and some small percent that go above that, those people probably know a lot about garbage collection already. I will come back to this point later as we talk about the memory sizes of applications and the trends with them. But keep this in mind, and hopefully this fits roughly what your experience is. So let's start off with why you should understand garbage collection. And I like to use a practical example for that. This is a real story that actually happened. Early in our pauseless garbage collection days with our Vega systems, we ran into a very good architect. And I define a good architect as somebody who can impose their will on a team. Before and more important than their ability to actually come up with good design, if they're not able to make everybody do and apply their design, they're not really an architect, they're just a philosopher. So early in our days, we ran into a good, strong architect that was able to impose a design pattern that was surprising to us. We were running into 18-second pauses in garbage collection in an application that, we would normally not even see 10 millisecond pauses in. And that was embarrassing at the time. We had to dig in to see what was going on. But when we dug in, we found that the collector was executing millions and millions of finalizers every time it was collecting. And as it was doing that, it was doing the finalization part as a stop the world thing because we had not yet engineered that into concurrency. So since then, we've addressed that too, and even applications that do that will run in a fully concurrent garbage collector on Zing. But at the time, that was a very large pause, so we're trying to figure out where it comes from. And as we dug into the application, we found that every single class written in a project that ran for well over a year had a finalizer in it. This was an architectural decision that was imposed on every single piece of software developed during a year and some in the process. Now, more surprisingly, the finalizers were doing not just nothing, but worse than nothing. They were literally putting nulls in every reference in the objects as it was going in order to supposedly help the garbage collectors. Now, for those of you who have a little experience with garbage collectors, you probably realize that this is probably the worst possible thing you could do to a collector. Make every object allocated have a finalizer and then have that finalizer run before it's collected. It's a wrong discipline if you're running on a garbage collected environment, but it's absolutely the right discipline for non-garbage collected environments. Clearly, when you come from a C++ or some other environment where reference counting is prevalent, having destructors and this kind of discipline around destructors is necessary. So shifting that architecture from a non-garbage collected environment to a garbage collected environment can often come with very, very bad consequences. This is a good example why from an architecture perspective, from a developer perspective, it is important to understand what garbage collectors do, what they're very good at, and what they need help with if any, or where helping them is probably a wrong thing to do. So with that, actual example, let's look at some of the things people seem to know or not know about garbage collection. There are a lot of common wisdoms out there, and I would say that a lot of the academic material out there is actually very good and very carefully written. But a lot of the content on the web seems to be the opposite of exact, often the opposite of true. And I see a lot of cases where people believe things about garbage collection that are not necessarily true. In some cases, those things are much better. The reality is much better than you might think. So, for example, garbage collection is extremely efficient. It is hands down the most efficient way to manage dynamic memory that there is. If you're going to allocate in free memory, there's no faster way, cheaper way, both in cycles and power and latency than garbage collection. And while that might sound controversial, I'll show you this with numbers as we go. The other part is that garbage collection collects objects reliably. All data objects will be collected. There's no need for help or like the finalizer example we showed before where nulls are put in references. Anything that you won't reach will be collected, whether it's a linked list or a circular linked list or a graph of hash tables or graphs of linked lists of hash tables. You don't have to worry about cycles. You don't have to worry about breaking links just to let the collector figure it out. In fact, doing that makes it work harder, not less. And on the side of things that the collector does that are usually worse than people think, there's obviously pauses. And yes, in most existing systems, there are inherent pauses of about a second per live gigabyte that come with garbage collection. It is not a question of if it will pause, it's a question of when it will pause. And most of the tuning exercises that you will be going through in most JVMs involve pushing that pause further and further into the future, making it more rare, and maybe getting it to the point where it's so rare that you'll restart the system before it happens. We see a lot of systems that are tuned to run so that it's only once every few hours. Sometimes it's once every few days, and you restart at night, and you're lucky. But that level of pause should be expected unless the JVM and the collectors have actually been designed to be truly concurrent, which currently exists only in one product, and I'll let you guess who that is. Now, in addition to pauses being there, one other very important problem that garbage collection introduces is a conflict between tuning and performance and quality. We're used to testing applications by setting a goal. The goal is usually passing some sort of test of quality and response time characteristics under load. We run that test for some amount of time, 20 or 30 minutes, and when we first try to run it at the desired goal, we obviously fail. So we tune the system and improve its performance until it gets better and good enough that we pass. Well, in regular systems that don't garbage collect, that tuning usually presents a pretty reliable picture. But in Java environments, what you often end up doing is taking a problem that happens every minute, making it happen less and less often, and as it goes, pushing it into the future. Now, as you push things into the future, you might succeed in the test, but production might be in pretty bad shape, and that is unfortunately a very common thing I see today in Java environments. Let's jump into some terminology and classification. We'll start with concurrent versus parallel. Now, these two words are often confused because they're somewhat synonymous, and in some languages, they even translate to exactly the same word. In fact, in some academic papers that are 30 or more years old, you'll find the word parallel to be used in the meaning that today we would use concurrent. So the confusion is understandable. This is a clear definition of the current meaning of concurrent and parallel. Concurrent means concurrent with the application. The collector is running while the application is running without stopping it. And parallel means able to use more than one CPU or more than one thread to execute. Those two terms are orthogonal. They have nothing to do with each other. You could be parallel and not concurrent. You could be concurrent and not parallel. You could be both, or you could be neither. Most collectors these days are parallel simply because most systems are multi-core, but parallelism and concurrency are two separate things. Let's look at some more terms, collapsing those two at the top. A stop-the-world collector is pretty much the opposite of concurrent. You can either be concurrent with the application, or you could stop the world while you're collecting and not let the application run. An incremental collector is a collector that takes the stop the world part, and instead of doing it as one big monolithic piece, it breaks it into pieces that are smaller, where it will stop the world for a little bit, then get to a point where it's safe to run the application again, let the application run for a little bit without the collector running, and then come back and stop the world again. And after doing a certain number of increments, it will complete a complete passive garbage collection. The opposite of incremental is monolithic, and there are garbage collectors that are monolithic or algorithms that are monolithic. And monolithic pretty much means once you've started, you cannot stop safely. And if the process is started, it has to complete. There is no way back. Now, the most important word in garbage collection is the word mostly. We use it a lot. And as a word, it means exactly what you think it means. It means most of the time. And it's usually used as a qualifier ahead of a good term to point out that the good term will not always be there. Unfortunately, in marketing terms, it's used ahead of a good thing to say the opposite of good. Mostly concurrent means sometimes stop the world. Mostly incremental would mean sometime monolithic. Mostly parallel would mean sometimes serial. So when you see the word mostly, both in technical terms and marketing terms, keep this in mind because the focus is usually on the opposite of the sentence, not on the sentence itself. Okay, now another clear separation between types of collector is along the precise and conservative line. A conservative collector is a collector that is not entirely aware of where all the pointers or references are in the world. Or if it does know where they are, it doesn't quite know if it's a reference or an integer it might be looking at. A collector is precise if it does know all those things, and preciseness is needed primarily, well, for various reasons, but primarily in order to be able to move objects. Because if we're going to move an object from one place to another, we have to change pointers that point to it. Pretty much every pointer in the world that could point to this object has to correctly be shifted. If we don't know where those pointers are, that would be a problem. And even if we know where they are, but we're not quite sure if they're pointers or integers, we couldn't change, it would be dangerous to change an integer that happens to have the same value as a pointer would, just because some object moved. So preciseness is needed in order to have long-lived collectors in most garbage collected environments. And most of the work around preciseness is not the collector doing too much work, because it's actually pretty easy to collect when you know where everything is. It's having the information to begin with, and that information comes from JIT compilers. The JIT compilers and runtimes literally develop information for every point in code that it might stop to garbage collect with a description of the entire stack and every register and every stack location that might have a reference in it. That information needs to be up to date. It needs to be correct. Even one mistake in it could corrupt the entire heap. And this is the kind of work that JIT compilers produce in addition to the code itself. One of the reasons that they need to be very carefully designed and tested. Now, all commercial JVMs use precise collectors, which is good news, so you live in a precise world today. But it's important to understand the difference between that and non-precise techniques that 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 will not be able to move objects around. Now, to be precise, we need those descriptions of where all the things are, and those descriptions are available at certain points or ranges of code. We call those points safe points, and you might have heard the term before. A GC safe point is a point or range of execution where a thread has a good description of all the state, including all the references. Um, it is safe for the garbage collector to operate on that thread knowing where everything is. When we say bringing a thread to a safe point, we talk about getting the thread to this point, the safe point, and not letting it get past it. And while that often means actually stopping the thread, there are good examples where that's not the case. JNI calls, specifically calls in a native code, are done at a safe point. And for the entire duration of the call, the Java state, the description of the stack that the collector is interested in, is completely stable. It's not changing. For example, you could be inside a matrix inversion call in C++ for the next 20 minutes, and you're at a safe point. A collector can collect, can manipulate and change, and look at your state for Java, and nothing is changing. If you call back from that code into Java in any way, you will be leaving the safe point and coming back. But it's important to understand that being at a safe point does not mean being idle. It does not mean the CPUs are not working. It just means that no Java visible work is being done. Now, a global safe point is a situation where all threads are being asked to be at the safe point at the same time, which is the only safe point most JVMs are doing. And that global safe point is the stop the world pause that you usually see. A very important thing about safe points is that they need to be frequent enough that they'll happen within microseconds of needing to happen. And the reason it's important for them to be frequent is if one thread might take a really long time to reach a safe point, say they're in the middle of some very long operation that doesn't have a safe point in it, and the collector or some other part of the JVM needs to get to a safe point for any reason, you could be in a situation where all threads are at a safe point already, but this one thread is not. The collector will not have started its work, so it doesn't even consider this to be part of a pause. But no work is being done and everybody's stopped, except for this one thread. This situation is unfortunately very common because there are optimizations and code paths in JVMs that are often rare but sometimes really long. Things like cloning or copying large arrays or certain types of loop optimizations could cause very long operations, hundreds of milliseconds in length, to happen with no safe point in the middle. And while those usually do not incur any hit unless garbage collection occurs at the same time, when garbage collection does occur, they are underreported. In fact, I said I won't be talking about flags, but in this case, you should know that the garbage collection logs cannot be relied on to report these stalls of everything before GC started. But there's one flag in Hotspot that you can use, which is print GC application stop time, which will report the inclusive time in addition to GC. And in fact, it'll report on all safe point times for any reason. I highly recommend people use that and rely on that number much more than they rely on pause times reported by garbage collection for other flags. So as we go through safe points, let's talk about what collectors do with this. So in all precise garbage collection mechanisms, all mechanisms that actually know where all the pointers are, there are three things that always happen. Live objects are identified, dead objects are somehow reclaimed, and live objects are moved at least once in their lifetime from one place to another. All three of these things will happen in every precise garbage collector on the market today. And while the first two are pretty obvious, they seem to be the definition of garbage collection, it's often not obvious to people that the third one happens as often as it does. Relocation of objects is a common thing and happens all the time. Good examples of all these three things in play are a mark, sweep, compact collector, where the collector does each step separately. Mark is the identification of live objects. Sweep is the reclamation of dead space in some way. And compaction is the moving of objects together. A different form of a collector that does this not as three separate things is a copy collector. In a copy collector, the objects are assumed to be found in something we call a from space. We look at all the objects in the from space and move everything we can find to what we call a to space, a different space. And we do that all in one pass. And at the end of that pass, we have an empty from space. So we've reclaimed that space. That's an example of doing all three things: identifying the objects, moving the objects, and reclaiming the space all in one pass, not as three separate operations. But these three things will happen pretty much in all cases. Now let's step into each one as a separate phase and look at the details. And I'm going to start talking about complexity here as well. So marking is fairly simple. It's an exhaustive operation, but it's a fairly simple one. We start from what we call the roots, which are usually the stacks and the static variables. And we follow any pointer that we find to anything we can reach and paint it alive, mark it with something that indicates that the object is alive. And then we look within that object for any pointers and we follow that, and so on and so forth, exhaustively until we no longer find pointers to things that are not alive. At the end of a mark pass, when we've exhausted everything we can reach, all reachable objects will be marked live, because that's what the mark does. And all non-reachable objects are going to not be marked alive. Now, there's a very important quality at this point that's worth noting. If an object is not currently reachable, there is no way for it to become reachable in the future. There's no way for me to have a reference to it if I can't reach it now that will appear in the future. And as a result, the dead objects are reliably identified regardless of the object graph shape. So it doesn't matter if there are circular lists here or some multiple references to things that are not cleared. If something is not reachable from the roots, it will be found as dead. So going on to the next phase. Sweeping is very simple. Once we've marked and found what's alive or dead, we sweep through the entire heap, take the dead objects, and somehow reclaim them. That usually involves putting them on free lists of some sort. Either one big free list or free lists bucketized by size. There are various ways of doing that. But sweeping invariably looks at the entire heap for dead things. And that means that from a complexity point of view, sweeping is linear to the heap size. And will grow with the heap size and shrink with the heap size, but will not be affected by the live set. Unlike mark, where marking is linear to the live set, we will mark only the live object. And you can grow and shrink the heap. It will not change the amount of marking work that will be there. What will change it is the amount of live objects that you have. Now going on to compaction, over time, the heap does get fragmented. It gets little holes in it because variable size objects come and go. Almost all applications in the world have variable size objects that they don't control. XML processing, HTML processing, pretty much any message processing includes variability in size that is not under the program's control, and as a result, fragmentation just occurs naturally. As fragmentation happens, we can get to a point where the heap might be 90% empty, but there's no one hole available for a 10 kilobyte object I might need. And at that point, we're left with either needing to break objects into pieces, which makes things really slow, or making bigger holes. And the way we make bigger holes is by compacting the heap and shifting things around such that more larger contiguous holes will be available. Compaction is pretty much that action, and in compaction we move objects together in order to make larger empty spaces contiguous. We call that relocation, the relocation of the object. In addition to just moving the objects, we obviously have to fix any pointers that point to those objects so that all pointers will point to the right place. And that is the remap or fix-up phase of collect compaction. Now, um, remapping an object is a fairly straightforward thing. You just take the object and move it somewhere else. But fixing all references to it means finding all the references and fixing them, which may involve looking at the entire heap for the one object we moved, which is why we don't move one object. We move a lot of objects and amortize the fix-up across all the object sets that were moved. Ideally, you want to compact the entire heap in one pass. That's the most efficient way to do it. But there are other ways to do it as well. So while this operation, the remap and the fix-up, is fairly heavy and is probably the largest pause you will see in a garbage collection, from a work perspective, it's still linear to the live set. The more objects we have, the more things we have to move, and the more references we have to shift. But heap size does not affect compaction size, compaction time. More live matter will, but larger heaps do not. So from a complexity point of view, it is important to keep in mind that, like Mark, compact is linear to the live set, not to the size of the heap. Now, the last mechanism I talked about before was copy. A copy collector, as I said, moves everything from a from space to a to space and reclaims the from space as a result. At the start, everything is known to be in the from space, and by following the routes and moving everything we can reach to the to space recursively, we know that at the end everything is in the to space and the from space is empty. Copy is done as a single pass, and usually it's a monolithic operation. And from a complexity point of view, again, it is linear to the live set. We only have to copy and move the objects that are live, and as we copy them, the references are fixed as we visit them because we're moving the next object and the next object around as well. So we described the basic mechanisms here and their complexity levels. Let's stop and look at some of their qualities. Copy is interesting. It's a very efficient mechanism. But in order to reliably complete, it actually needs twice the amount of memory as the live set. And the reason for that is that at the beginning of a copy, when your from space is full and you want to collect it, you don't actually know that there's anything empty in it. The entire space might actually be full, and you may have to copy all of it over to the to space. And since this is a monolithic operation, you have to pretty much start knowing that the to space is as big as your entire from space. That quality is somewhat annoying from a memory efficiency point of view. But there are other efficiency factors that make it worthwhile, and there's some interesting ways to get around this problem we'll get into in a second. Mark compact without the sweep, which is a technique where you mark everything and then compact things by moving them elsewhere region by region, but without a sweep operation, will typically require the same 2 times the maximum live set in order to fully recover everything in one cycle, but it's not monolithic. You do it region by region, and as a result, you could stop at any point and decide that if there's not enough room to continue, you'll just do it in another cycle. That means it could live on less memory and come closer to the edge of memory. Mark sweep compact, and this is often called in-place compaction, requires sweeping, is the act of compacting things in place. Usually you can imagine taking the entire heap and saying, once I know where everything is alive and dead, I'll just move everything over to the left. Push it against each other, closing up all the holes so that they'll squeeze together. You could do that if you sweep and you know where the holes are, and you could do it without requiring any additional memory except for a tiny bit of temporary memory. That means that Mark sweep compact from a compaction perspective is more memory efficient in most implementations. And then we know that copy and Mark compact are both linear only to the live set. but the mark sweep compact is linear in addition to the live set to the heap size itself. So as you grow the heap, complexity will grow. And then there are variations of mark sweep compact where compact is not done most of the time, where we attempt to delay compaction. That is a combination that happens. And I already mentioned that copying is usually monolithic. Now, with those qualities together, we can step into something called generational collection, which most people have been exposed to because virtually all commercial JVMs use it. In generational collection, we leverage something we call the weak generational hypothesis, which was observed about 30 years ago, and it's basically the observation that most objects tend to die young. Now, this is not to say that most objects are young. It's that most objects tend to die close after we've allocated them from a dynamic behavior point of view. Now, with that knowledge that most things die young, we could try and use what we know about complexity of different allocators and different collectors in order to achieve extreme efficiency. If we know that if we focus our collection on the part of the heap that is known to be young, and therefore known to be sparse because most of it is dead, we can apply a collector that is linear only to the live set, and that's a very important point, the linearity to the live set as opposed to the size of the region. And in doing that, because the space is sparse, we gain extreme efficiency. If only 1 or 2% of the young space is actually live, then I will only copy 1 or 2% of its size somewhere else, complete very quickly and not waste time on the rest of the space. It'll just be reclaimed as one big chunk. Usually this is done with a moving collector, a copying collector. And it's extremely efficient. But in order to keep it going and keep it efficient, we have to keep the quality of the young space being sparse. And we do that promoting objects. So promotion is the act of taking objects that have been around for a while in the young generation and making sure they don't stay there and they move on to somewhere else, the old generation. Because if they did stay there, they'll start accumulating and the sparseness will go away. And with that sparseness, all the efficiency of the young generation will go away. Now, I see people tuning collectors in various ways, and one of the mistakes I often see is people trying to make sure that nothing ever gets promoted, even though they have a lot of objects. They keep everything in the young generation and try and tune things that way. And while that might work to some degree, what you're actually doing is moving into a pure copy collector where the sparseness is not a quality of the system anymore, and efficiency goes out the window. So efficiency here is purely there if the young generation is sparse. It relies on promotion. It relies on actually moving things away from this space if they stick around, because without that, the efficiency is destroyed. And this generational filter is extremely effective. The efficiency here is usually an order of magnitude or maybe even more. 10x or 20x throughput improvements in collection is a very common thing to see compared to single generation collectors, which is why pretty much all commercial JVMs use generational collectors today. It's not really practical to run at today's CPU speeds and allocation rates without one. Now, in order for generational collection to work, we need something we call a remembered set. A remembered set tracks references into this part of the heap that we're going to collect so that we can collect and focus the collection just on that part. Remember, everything we talked about so far assumed we're looking at the entire heap. But in order to collect only part of the heap, we need to consider anything pointing into that part from other parts of the heap to be roots. So in addition to the thread stacks and the static variables, we need to know about any pointers from the old generation into the young generation. The remembered set is that set of pointers, the set of pointers that are pointing from outside the young generation into the young generation. And to be more precise, this is the generational remembered set. There are other forms of remembered sets used for other types of collections, and the two are often confused. Now, the interesting thing with using the young generation as a copy collector for the young generation is you no longer need the 2x memory thing we talked about before, because you can optimistically assume that the young generation could fit into a much smaller survivor space than 2x the size. And if you're wrong, you'll just promote whatever spills over. So as long as there's room in the old generation for your young gen from space, you can start and reliably complete a collection, even though it's monolithic, without having to keep aside twice the Eden size in space. Now, from a tuning perspective, I said I won't be giving people tuning advice on flags, but time in the young generation is important. You already spoke about why you don't want to be promoting things out of the young generation too early into the old generation. Sorry, too late, because if you do that, the young generation will stop being sparse and the efficiency will drop. But you also don't want to promote things too early. If you promote objects immediately as they are found by the first garbage collection pass in the young gen, a lot of very recently allocated objects would be promoted that would not have been copied if they had a chance to die a little by letting them live a little longer. So the recently allocated objects just before the collection started are things that you tend to want to keep around for at least one cycle to give them a chance to die. So collectors usually try and keep objects around for at least one cycle or at least some amount of time before promoting them. And that's usually controlled by something called a promotion threshold. The reason you don't want that set to 0 is because doing that usually increases the promotion rate by an order of magnitude. So it's not good to try and bring it down to 0. Even though you have the ability to tune it that way, it's not necessarily a good idea. I'm going to run quickly through this so we can get to the interesting questions and parts, but the remembered set is usually is basically maintained in most JVMs using a write barrier. Every time we store a reference to memory, we track that reference in some remembered set tracking system. In Hotspot, that tracking system is called a card table. Pretty much there's a bit or a byte somewhere for any region in memory that might have pointers from the old to the young. And the write barrier just keeps that correct. It is pessimistically correct because every time there might be a reference there, you have to account for it. And when you clear a reference, you don't necessarily know that you no longer have a reference there to the young generation, or when you change a reference to something else, you don't want to have to correctly and atomically and concurrently set that. So the various techniques used for card table management usually involve a blind write of some sort or a checked write, but the assumptions are pessimistic. There was a pointer there at some point. There might still be a pointer there, and we will need to look at it as part of the root set when we do the collection. And there are various techniques around cleaning those or keeping them more precise that we won't get into now. Now, with all that background, I'm going to start talking about how these things come together. And in most commercial JVMs, you will see a generational collector. And within the generational collector, you'll see a young generation that is usually a copy collector, usually a monolithic stop the world copy collector. Now, at this point, I've defined every one of the terms that we're using in the slide, so hopefully they're all understandable. The old generation is usually some form of a mark sweep compact. It's very rare to see a copy collector for the old generation. But variants of the mark compactor, mark sweep compactor around. The old generation could be any combination of, it could be pure stop the world or concurrent or mostly incremental and various combinations. Now I want to pause here for a second, pun intended, and see if we have any pent-up questions about that have come up so far before we go into some more points about efficiency and non-stop the world mechanisms and then classification.
Okay, we have a couple of questions. They're related on the same topic. The question is about what does it mean when an object is reachable or not reachable? Like, can you define that?
So when I say that an object is reachable, that means that if I start from the roots being static variables and the content of the thread stacks, and look at every pointer there and follow that pointer, and then look at any pointer in the place that I followed to and follow that, I can eventually reach the object in question. A non-reachable object is an object that doesn't have a path from the roots to it through any combination of pointers. So the mark phase, the trace phase I talked about before, is the act of actually doing exactly what I said there. You start from the roots and you follow everything and you mark what you've reached, and then you follow from there and you keep marking live anything you can reach. You mark it reachable. And when you've exhausted that, when you no longer find pointers to things that are not already marked as reachable, you know that the work is complete. It's a finite, monotonically progressing piece of work. And at the end of that phase, you've reached everything you can reach, and things that you can't reach at that point cannot become reachable again because there's no way to get to them.
Okay, and a related question: what does it mean about when you say you're following from the root to follow the references? Like, what is this root and where is that stored?
So it's roots in plural, and the roots are basically the static variables of your application or of the JVM and the content of the thread stacks. So there's some static variables that are known by name. You can just, look them up by name and they're there. So they're reachable not through a pointer. Those are absolute roots because if there's a pointer there, you can reach through them. And then if you look at any thread, the thread has variables on the stack, temporary variables, various sorts, stack variables, and those may also have pointers in them. So if you look at a thread's state, the thread includes pointers to things. Outside of those two things, static variables and the content of thread stacks, there is no place you could start from to look for a reference. So if something is not reachable from one of those two things, it's not reachable at all. And those two things together are what we consider to be the roots. I also used the expanded term for roots when I talked about looking at a part of the heap, like the young generation, where from the point of view of that part of the heap, anything pointing into it needs to be a root, and that includes things that point to it that are in other parts of the heap that are not it. So, for example, for the young generation, all pointers in the old generation that point into the young generation are part of the root set of pointers.
So, related question, this is my question. So if I'm in the body of a method and I create an object and then my method exits, is that object created, is that during the young generation at that point?
If you're in the body of an object and you create an object and exit, assuming you create it using new in Java, then you've allocated the object. In most implementation, that allocation will be in the young generation. It could be, it's in the heap somewhere, it's not on your stack, but it could be in the old generation or in a single generation collector, it's just in the heap. But for example, in some JVMs like Hotspot, if you allocate a very large object, larger than a couple of megabytes and often larger, the size is much smaller than that for the threshold, then it won't be allocated in the young generation, it'll be allocated directly in the old generation. But most small objects are allocated in the young generation.
Okay, that's all the questions we have right now. If anyone else has any questions they want to pick up later, if you post them in the chat window, then we'll pick them up again later on.
Good. Okay, so we'll continue. I'm not going to talk about all these terms or metrics in the next slide, just to highlight that monolithic stop the world is an important term. But one other thing to highlight here is in garbage collection terminology, we have this thing we call the mutator. The mutator is pretty much you or your program. And we call it a mutator because it mutates the object graph. It changes the shape of the way objects point to each other. So any change to a reference, including the allocation of a new object, and which means you've added a reference to it somewhere in the root set. Um, um, any allocation of an object, any change to a reference is a mutation of the object graph. And I will use the term mutation as we go. Some important metrics include things like allocation rate, which is pretty intuitive because it's how much we make per second. But allocation rate is interesting because it tends to be a direct side effect of work. So whatever work you do, whatever your application does, I could pretty much predict that if you double its work rate, you will also be doubling its allocation rate. Allocation is just a side effect of work, or sometimes you can think of it as work is side effect of allocation. Mutation rate, the rate at which you change things in the heap, is also tends to be linear to work. And the faster your application runs, the more things per second it does, the more mutation will be happening to the heap. That's an important metric for collectors that are sensitive in some way to mutation rate. And then time for doing different things is also important. Now, I mentioned before that garbage collection is extremely efficient. I intentionally used terms that would make people question that statement. It is the most efficient way to collect, to manage memory. There is no more efficient way of doing it. It's impossible to beat garbage collection from an efficiency perspective with things like a malloc or free or reference count system. Let me explain how that works and why that statement is absolute. Look at this graph and imagine that the y-axis is the amount of CPU that we spend on garbage collection, and the x-axis is the size of the heap. Now, there's a point on that x-axis, which is the live set, the amount of memory we need for the actual objects in the application. And if all we had in memory in heap is that amount of memory and no more, or that amount of memory and a couple words more, then we know we would be thrashing. We know that every time we need a word of memory, we'd have to find it in the entire live set. Imagine live set was a gigabyte and every allocation of a word needed to scan a gigabyte in some way to find it. It wouldn't matter which algorithm we used. It would be extremely inefficient. But the other end of the spectrum is pretty easy to understand. If we had infinite memory, we would never have to garbage collect, which means we would spend 0 CPU on it. And between those 2 points, the 100% CPU and the 0%, there's a perfect 1 over x line that connects the two for any collector that is linear to the live set and nothing else. So as long as you use algorithms linear to the live set, your efficiency doubles with every doubling of empty space in the heap. So having 4 words empty in a gigabyte is still pretty bad, but it's only half as bad as having 2 words empty. And if you have a efficiency problem where you spend 20% of your time on garbage collection and you have a half gigabyte of empty heap and that's what it takes, 20% to keep up with that, I could pretty much guarantee that if you double that to a gigabyte, your efficiency will double. You'll half the CPU time to 10%. And then if you double it again, you'll half it to 5%, double it again, half it until you just don't care anymore. So you have the power to change the efficiency to any number you want, all the way down to 0, and all it takes is memory, empty memory. So by increasing empty memory, we increase the efficiency of garbage collectors. This is a very, very powerful knob. It is used by the young generation, and it is why the young generation is efficient to begin with. But it can also be used for old generation in collectors that are linear only to the live set and are not linear to the heap size. Now, Why isn't this used all the time? Well, this is just text that says what I just said. Um, but we're able to exchange empty memory for CPU power here. And in doing that, we control efficiency. We control the amount of work we do to collect. We also control the frequency of pauses. So the less often we have the garbage collect, the less frequent the pauses will be. But we do not reduce pauses by increasing empty memory. We just reduce their frequency. And pause time is not a function of empty memory, in a good way at least. It doesn't get better with more empty memory, but it could get worse if the collector is in any way linear to something in the heap size. So in most cases, you'll see this knob used for efficiency in the young generation to some degree. And it does provide some efficiency in the old generation in collectors, including Mark Sweep Compact, because parts of them are linear to the live set. But the reason you don't usually see this knob used to the extreme is because as you grow the total heap size for the old generation, the pause time for the old generation will grow with it. And usually the tuning parameter that most people spend their time on is not efficiency of garbage collection and CPU time, because that's easy to control here. It's trying to address pauses. And when pauses get worse, you don't want to go there. You're trying to go the other way. So there is a knob here. It's very effective. Increasing empty memory will increase efficiency, reduce CPU time on garbage collection, increase the efficiency of the system overall, but it's only useful as long as you can keep pauses under control. Any questions on that point? Because it's an important one. Looks like we're good.
Yep, no new questions yet.
Okay. Okay, so I'm going to go through a couple of examples of non-stop the world things. So we talked about simple stop the world garbage collection so far. But stop the world is a bad thing intuitively, and there are things people have done to work around them. The first thing to look at is how do we find the live things without stopping the world? The description I had before was if nothing is changing, we can find all the live stuff. But what do we do if while we're trying to find the live stuff, we want the application to run and the heap will start mutating under us? Well, there's basically a race. It's a single classic concurrent marking race in which the marker is going around marking things, finding what it can reach, and as it's doing that, the application could move a reference to a pointer that the collector has not yet seen and deposit it in an object the collector has already visited, and then get rid of all other copies of that reference. So the object is still alive, it's still being referred to, but the collector in its normal pass wouldn't have seen that reference. And if we allow the collector to complete, and for that to happen, we will get a heap corruption. We would throw away a live object. That's not a good thing, and no collector can afford to do that. So in some way, this race has to be intercepted, and there are various ways people have built to intercept them. Every concurrent marker has to intercept it. A common technique is mutation tracking. So using multipass marking and mutation tracking is something you see in several collectors. The technique pretty much goes like this. While the collector is doing its regular marking pass, any mutation, any change to any reference is tracked in some way. And when we finish the first marking pass, we'll go and look at all the mutations that happened during that pass and go to every reference that was mutated and check to see if we need to visit that because it might have raced with us and hidden something. And while that can still happen concurrently and we can still track mutations as that's going, when we finish that pass, we'll have to go back and look at the list again. And at some point, we hope that the list of mutations is small enough that we could just stop the world. That's part of the mostly part here, and catch up. Now, for those of you familiar with CMS, the concurrent mark sweep collector, the regular mark is exactly this. The marking pass is concurrent, but mutations are tracked in a card table. Before the end of the CMS phase, there's a concurrent cleanup phase where you try and um, visit those mutations and clean them up. But then at the end of that, there is a remark phase that is done as a stop the world operation, in which we do that final catch up with all mutations that have happened. Um, this is very effective, and it works to a large degree, but it's sensitive to a very important metric. It's sensitive to mutation rate. So when your application is near idle, the concurrent marking is very, very effective when nothing changes. But as more and more things change because your load is higher and higher, there's more and more work and more mutations to track, to the point where you might fall behind or may not be able to catch up, or just take long enough that you ran out of empty memory anyway and you may as well pause. But for low throughput or up to a certain throughput of mutation, this technique achieves mostly concurrent marking. Another mechanism is incremental compaction. In this mechanism, the attempt is not to avoid stop the world, but to slice it into pieces. So the idea is we have a big stop the world pause for compaction. Can we, instead of doing it as one big monolithic operation, can we break it into a lot of smaller ones in between which we'll let the application run for a little bit? The technique for doing this is with a different form of remembered set. The heap is sliced into a lot of regions, usually a megabyte or more per region, 1,000 regions for the heap. And in order to compact one region, move the objects away from one region, we don't have to scan the entire heap for references into those objects. We just have to scan references that are in regions that we know point into this region. So if we track region to region remembered sets, if we know which regions contain which pointers to which other regions, and we know that some regions are not pointed to from everywhere, we can go after those regions and say, if I relocate this region, then even though there are 1,000 regions in the heap, only 17 of them point here, so I could relocate this region's content and then scan 17 other regions, and then safely know that I've addressed all pointers. The collector will go around and look for sets of these regions that together have a remembered set that is fairly contained, that can be hoped to be scanned within a target pause time. And when it finds a set like that, it will compact just that set, scan only the remembered set to it, and then let the application run again, and then stop the world again for a different set. It'll obviously start from the sparse parts of the heap, which is why it's called garbage first. And because those would be the parts that have more things to recoup by scanning regions that are hopefully less and less popular. But it has two little issues. The first one is complexity. So unlike the rest of the places where we've seen complexity that is linear to something like the heap size or the live set, in this case, the work can actually grow to the square of the heap size. And the reason for this is that as the heap gets larger and larger, the number of regions that point into any one region grows with that. The things in the heap are fairly randomly distributed, and there's no actual thing that puts them in certain places, because collection is what puts them in places. So as you need to collect a heap and it's got a certain amount of live and dead things in it, the likelihood that there's a pointer in a region pointing to some place grows with the number of regions. So the more regions you have, the more things point into you is the simple way to look at it. And obviously the larger the heap is, the more such regions there are to compact to begin with. So as a result, the work needed to do incremental compaction when you're looking for a certain fixed size of pause will grow to the square of the heap. So as you grow the heap size, you are left with a choice of either growing the complexity of the work to the square of the heap, which means 10 times the heap, 100 times the work, or you're left with relaxing the pause constraints, allowing larger sets of regions to be collected together and accepting larger and larger pauses. The other problem in this mechanism is what we call the popular object issue. The regions that are popular that have a lot of other regions pointed to them are ones you don't want to collect. You probably avoid collecting at all costs. And over time, more and more of these will occur because as you don't collect them, they stay popular but sparse, and more regions become popular, and at some point you have to fall back on something. But this is a good way to delay the compaction, the eventual full compaction of the heap, and do it incrementally for a pretty long time. Now, when I use the word delay, I use it intentionally. You can look at the last 15 years or so or longer in garbage collection and in Java and see that we've incrementally added more and more techniques to help delay the inevitable bad thing. We added generational collection. It's great for efficiency. It also is good for delaying the really big bad pauses and replaces them with small ones. And then once we have a generational collector and we have to eventually collect the old generation, we've noticed that most of those dead things might be able to be collected in place. Maybe we can recycle them without compaction. So the concurrent mark sweep collector focuses on that approach and collects in place. But eventually fragmentation occurs and we have to fall back to something else that compacts, and that's where G1 and similar collectors have looked at collecting by compacting and incrementally compacting. But eventually we have to deal with popular objects and complexity and other things that as we grow things becomes a problem. Now each one of these is a very good additional filter. It helps us push the big problem further up the hill. But each one of them is a delay, and that's an important thing to understand. So I'm going to go in and with that look at the actual collectors that we have in actual common JVMs today. And I'll mostly focus on the hotspot JVM and mention others as we go. So the most commonly used collector in the world today for Java is, I've already covered the types here. The most commonly used collector in the world is the parallel garbage collection collector on servers. It's the most popular one simply because it's the default one. If you don't use any flags around garbage collection, this is what you will get. It's a classic monolithic stop-the-world copying new gen with a monolithic stop-the-world mark sweep compact old gen. And we covered exactly what that works like. It's exactly the mechanisms we talked about in the first. Now, moving on to other collectors, the concurrent mark sweep GC, or known as CMS, collector is another popular collector in servers. It's usually used when people are trying to avoid the big, bad, old-gen stop-the-world pause that is multi-seconds on multi-gigabyte heaps. Now, the new generation for this collector is classified exactly like the new generation for the previous one. It's a stop-the-world monolithic copying new gen. So there's nothing concurrent about it, and the concurrent mark sweep terminology is used purely to describe the old generation. Now, the old generation is made up of a mostly concurrent non-compacting old gen. It uses that multi-pass concurrent marking we talked about. It has a concurrent sweeper. But since it doesn't compact, it falls back to a full collection when it does need to compact. Whenever you see the messages promotion failure or concurrent mode failure in your GC logs, that's what's going on. The collector is falling back to a full stop-the-world GC. So while it's mostly concurrent, the other side of mostly is full stop-the-world. And in addition to concurrent mark sweep, we have the hotspot G1 collector, which has become an actual production collector in the last probably less than a year in Java 7. The G1 collector is similarly a monolithic stop-the-world copying new gen. So the new gens for all three collectors are identical algorithmically. But their implementation is slightly different and flags are slightly different, but from a technique perspective, they do exactly the same thing. Monolithic stop-the-world copying. G1 has a mostly concurrent all-gen marker, so the marking part of the collector is concurrent to the same mostly part as CMS. So it'll do this multi-pass thing, track mutations, and And in addition to doing that, it tracks intergeneration relationships in order to enable the other part of the collector. Now, as opposed to CMS, which does not compact at all in the alt-gen and falls back to full GC, G1 does compact the alt-gen. In fact, that's the only way it frees memory. And it does that using an incremental compacting technique. Now, this is a good delay technique, but to avoid confusion and argument, I quoted from its design objectives here. It was designed to avoid as much as possible having a full GC, which means that it falls back to full GC when those delay techniques fail. And they do fail eventually, but it's a fairly good filter. People have been playing with garbage first tuning for the last year. I would say that my experience is that CMS is still better than garbage first in most environments, but people are learning more and more about how to tune it, so you should be looking at both and understanding both, probably, if you want to understand the world of tuning garbage collectors, at least. Okay, so with those with those classifications behind us, I'd like to take a short pause here again and see what questions have come up so far.
Okay, a couple of questions. How can you determine which garbage collection algorithm you should use?
Well, I don't really have an answer for you for that one. I could give you examples of trade-offs, but really this is the part where understanding what they do and then thinking of what you need the system to do is important. So for example, if you have an application with a very small heap, a couple hundred megabytes and only a few tens of megabytes of live set, the default collector is probably going to do a great job for you unless you need better than tens of milliseconds of responsiveness. But as you grow the heap size and you grow your application requirements, you may find that you don't like the idea of having multi-second pauses, that users are annoyed or SLAs are failed or queuing systems start acting badly and clusters fail over. And those are reasons usually people end up spending time on pauses. At that point, you can do things to tune your collector, try and reduce the occurrence of pauses. And you can also switch to another collector that might help you reduce those pause rates as well. So for example, moving to CMS is a way of dealing with reducing, or a way of reducing the frequency of multi-second pauses in the alt generation. It usually doesn't have any significant effect on young generation pauses. And if those are the problem, you have to deal with them. G1 versus CMS, I don't really have good tips on. Today, I think CMS is much better understood, but both of them are collectors that try to do better than just stop the world every time for multiple seconds every time you need to collect the alt-gen. And they do achieve a delay technique for that. Without them, you will often run into an alt-gen collection that's multi-seconds every few minutes, and with them, you could probably run into it only once an hour, maybe once every few hours. If you're in the more latency sensitive part of the spectrum, so for example, if you're in the telco or messaging or trading world, these multi-second problems are not the ones you're really dealing with. You're probably dealing with young generation pauses and and trying to somehow reduce the young generation pause. And there are various techniques for shrinking the young gen to reduce the size of the young gen pause or increasing it in order to reduce its frequency, and there are trade-offs between the two.
Okay, so you could take a best guess based on understanding the characteristics of each one. Would you suggest then, would a good approach be like during performance tuning to pick one and then monitor the behavior and then see how it goes, and then try a different couple approaches and just see what their differences are?
So talking about regular JVMs, I would say that if you're entering into garbage collection tuning, you should plan on it taking a while. It's usually not something that is done in a few minutes or a few tests. In fact, one of the fortes of what we do at Azul is, as we'll get to that collector too, our collector is built to require very little tuning, if any, and that's partly in order to cut down on the significant engineering time that's involved in figuring out which collector and which settings to use, and the need to adapt that every time you change your application. But if you are tuning the collector, you should be spending time studying the behavior of the system, measuring it, and iteratively playing with it. Usually there are no good out-of-the-box settings that are good for everything in the regular hotspot collectors. And I will contrast that with Zing later.
Okay. One more question. How do you actually select which garbage collection algorithm you want to use? I think this is talking about like the switches.
So there are various switches for the JVM. They usually have a -XX colon ahead of them. If I flip back here to these collectors, I actually used the name of the collector. See the parallel GC, conc mark sweep GC, and G1 GC. Each one of those is the actual name after the word use. So -XX colon plus use G1 GC does this one, and plus use conc mark sweep GC does that one. You can find those by Googling GC tunings or settings for hotspot pretty much anywhere. So you can tell the JVM which collector to use. Obviously, you need the collector to be available on it, but all three of these collectors are available on the hotspot VM for Java 7, for example, everywhere. For Java 6, G1 is not available, but the other two are.
Okay. There's a couple more questions. We can queue those up for the end if you like, if you want to move on.
Let's take one more and then keep going.
One more? Okay. All the different types of garbage collection algorithm we've talked about so far, are these all typically supported by all JVMs, or do some support others?
So I used terminology from the hotspot JVM, which is the Oracle JVM, the OpenJDK JVM, and Azul also supports hotspot as well. Other JVMs out there include the J9 JVM from IBM and the JRocket JVM. The names for their collectors are different, but the terminology is the same. So for example, the J9 JVM has a collector called the balanced collector that shares the qualities of the G1 collector here. It has a mostly concurrent collector that shares the qualities of CMS, and it has a stop the world parallel collector that shares the qualities of parallel GC. I didn't name the specific names for them here. Similarly, the JRocket JVM has both a stop the world parallel, a somewhat concurrent or mostly concurrent old-gen, and it has something it calls the deterministic GC, which is not quite G1 because it's not generational, but it uses a similar technique of incremental compaction in a single generation. So this is not an exhaustive list, and obviously there are a lot of other JVMs in the embedded world and academic world that I'm not covering here, but I used primarily the hotspot JVM terminology, which is the most commonly one used. Okay. So I'm going to keep going with this and then we'll get back to some more questions. So remember I talked about application sizes, and I guess that most of you are dealing with applications that are in a fairly well predictable range of sizes. The interesting thing is that when I pose this question to a large audience, I usually get all hits within the circle without even asking what the application does, whether it's a web application, a messaging application, a trading application, whatever it is. Excuse me. And this is actually an interesting symptom because I'm basically saying we're not using memory effectively and we're using very little memory. Servers today are much bigger than applications, which is not a normal thing in history. A server, a very cheap server today, a $4,000 server, has more than 10 times or 20 times almost the memory size of most Java applications, which is an anomaly in history because we used to have applications that would easily saturate the servers we buy. we would keep them to a third or a quarter of the server size, but the servers were usually the challenge. We'd always want bigger and bigger hardware. And these days we want that hardware, but we seem to not be filling it up with individual instances. In fact, you could state that the application memory wall is the observation that application instances, as opposed to entire applications, are unable to make good use of server memory and somehow have to use server memory in other creative ways, like creating multiple little copies of themselves. Now, the size of an application as a percentage of a server is rapidly dropping. It has been rapidly dropping for a decade, and it's going faster and faster. A common question is, okay, how much memory do we actually need? Do we need that much? And in order to avoid the argument over that, it's easy to show that this question comes up every once in a while, and it's usually answered very quickly with history. 640 kilobytes was certainly not enough for applications, and we're way past it. And there isn't really a question of whether one of these other numbers is the right number. It's a moving target. It moves at about 100x a decade because that's how fast Moore's law moves. And a way to depict that is to look at kind of a graph of what I call the tiny application history. The tiny application is the one that would be so small that you would never break it into pieces, or if you did break it into pieces, you'd be too embarrassed to tell people about it. For example, we could probably all agree that a 1 kilobyte array, sorting a 1 kilobyte array, is something we don't need a 1,000 node Hadoop MapReduce environment for. And we could do it on our phone 1,000 times a second. And that was true all the way back to 1990, not with the phone, but at least not distributing it. Uh, but but the right at some size, the significant distributed system is the right one. If I was trying to do an exabyte array and try and sort that, the only practical way to do that would have been to distribute it. The point at which you distribute is usually at some significant respectable fraction of an affordable computer. And back in 1980, 100 kilobyte was already tiny. You could run that on a VAX 11780, and you didn't have to break it into pieces. You could for academic purposes, but you wouldn't do it for practical reasons. A decade later, 100 times that, a 10 megabyte application fit comfortably in entry-level servers that were 32 to 64 megabytes in size. And they were easily purchasable, and we didn't need to break that apart. But a gigabyte was a big problem then. And a decade later, a gigabyte was what we built the web on. WebLogic apps with 1 gigabyte heaps on 2 to 4 gigabyte, 2 to 4 core servers is what the dot-com boom came up with. And at that time, we also learned how to distribute across servers. We were able to do a lot of instances, load balance them, spread load around, and shard things. So we're able to be much bigger than a server could be by using those techniques. But here we are in 2013. A 256 gigabyte server is cheaper than all these servers combined. And the natural point today would have been about 100 gigabytes for an application we wouldn't bother distributing. But we clearly stop at a much lower number. And that's what I call the application memory wall. It's the fact that about a decade ago, we stopped growing instances. We used to be able to do 2 gigabyte heaps more than 10 years ago, and that's still where most people stop. 2 to 4 gigabytes is where they don't push any farther. If they have to, they go a little farther, but they have pain going with it. And that situation is not sustainable. When we have a 5 terabyte computer that costs $3,000, talking about instances that are a few gigabytes each would be just as silly as talking about 640 kilobytes now. In fact, arguably, it already is silly to talk about a handful of gigabytes and to consider 10 or 20 gigabytes a big number when a cheap computer is an order of magnitude higher than that. So what's going on? What is it that's causing this flattening? Well, it's basically garbage collection. It's the clear cause, it's the clear link between responsiveness and scale that's stopping people from building larger things. So as long as garbage collection will pause, and as long as that pause grows with the size of the heap, The size of the heap will remain limited by the amount of pause we're willing to accept. And since we are building more and more interactive applications, and more the business applications in the world come with better and better responsiveness expectations, we're building more and more pressure on the heap size, actually in a downward trend rather than an upward trend, certainly as a percentage of server size. Now, within garbage collection, it is not garbage collection in itself that's the problem. Garbage collection is efficient. Applications running on garbage collection environments are fast. They have very good averages and percentiles. It's usually not even about these minor GC events unless you're in low latency or trading, where that's a different discussion, but it's a very interesting one. And it's also not about whether or not, or how frequent the very large pauses are. It's the fact that they happen. It's the fact that people just don't want to build or explain to their customers why their system pauses for 7 minutes several times a day. And that's just not being acceptable. And because of that, we don't have 100 and 200 megabyte heaps, gigabyte heaps is a common case today. Now it's not impossible to run those, and people will spend a lot of time tuning them, but we seem to be staying away from this in a very significant way. Now, when we look at monolithic stop the world GC, we can try and figure out, what to do about it, and this is the most common thing we can do about it. Try to ignore it. A good way to try to ignore it is to test for only a little while. If we run a test and we tune it, we could get it to run for 40 minutes without a problem. But if we expand the time, we'll see some spikes. And if we expand it to days, we'll see a lot of spikes. And every one of those is a failure or generated call. And this is just, clearly a bad situation that everybody tends to have to live with. Another way to deal with this is to convince ourselves that, maybe it's not that bad, or to use nice language to describe the problem. Remember when I used the word mostly a lot, and mostly is, by the way, a way to describe academically the algorithms, but marketing has kind of run away with it. All these are statements from actual JVM technical materials about garbage collection. The top one is my favorite one. Guarantee a worst case of 5 milliseconds 99% of the time. Here it's worth noting that 1% of 1 hour is 36 seconds. And it's okay to pause for 36 seconds once an hour and you still meet this guarantee. In a low latency world where milliseconds matter, you can pause for 36 milliseconds 1,000 times an hour. That's every 3.6 seconds, and still meet this guarantee. But it is a guarantee, and it's an honest guarantee, and it makes people feel good. It just is kind of useless from a practical perspective. The words mostly, fairly consistent, and typical are other ways to achieve the same. So whenever you read those statements, what I want you to do is think of why the word is there and read it in the exact opposite of what it says. Fairly consistent means sometimes this will be terrible. Typical pauses will be small means sometimes they will be very big. So keep that in mind. You can actually measure things, and there's a tool that I have put up as open source. It's on GitHub. It's on our website as well in binary form. It's called JHiccup, and lets you actually get pictures like this of what's really going on in your application. It'll run on any Java application, on any operating system. It's a Java agent you add to your system. It can run in production. It's virtually zero cost. And it basically logs a little event every time a JVM stalls. All it does is measures whether or not it can run and do nothing. And it logs when it can't, and it produces these percentile pictures and pauses over time pictures, which are very useful for studying what your application actually does, as opposed to what it says it might do. In JHiccup does not measure your application response times. It measures the platform your application runs on, the JVM, the hardware, and everything in between. It doesn't know if a reason for a glitch here is a GC pause or a power glitch or hypervisor freeze or something else, power management. It just logs the fact that things weren't running, and since garbage collection tends to be a very dominant reason for that, it will usually align well with your garbage collection behavior. Now, we talked about stop the world. We talked about the memory wall. Well, how do we get past this? We need to eliminate the link between responsiveness and scale if we're going to get back on the scale curve. If we're going to keep using hardware the way it's produced, and if we want people to keep producing larger and larger hardware for us. So responsiveness needs to be unlinked from things like heap size and live set and allocation rate and mutation rate, or talking in application terms from transaction rate, concurrent user counts, data set sizes, and the rest. You should not need to worry that pauses will get twice as bad when any of those metrics grow twice as big. We need to unlink them completely and go back to the way things used to be in the 80s and 90s, where uptime was expected, pauses of these sizes were not even thought of, and we didn't have this kind of link. We could just grow our computer and grow our applications with it fairly well. Now, in order to do that, we have to completely eliminate stop the world fallbacks. It is not garbage collection that's the problem. It's the stop the world part of garbage collection that's the problem. And within those stop the world problems, here are the three things that need improvement or the industry has worked not enough on. In Zing, we've worked on all three of them, so we know a lot about them. The first one is robust concurrent marking. Be able to stay concurrent not just under low loads, but under high loads. As your system comes under stress, that's when it is most important for it not to pause. And you need an algorithm and a mechanism that will keep going no matter how hard you push it, up to the limitations of the computer as opposed to the limitations of the algorithm. You also need compaction that is not monolithic stop the world. And here, while incremental stop the world is being attempted, it is clearly showing that it's just a delay tactic. It's able to buy a little more time between pauses, but it increases complexity and it can only last this long. Going to true concurrent compaction will allow us to get away from pauses that are compaction related and really deal with heap sizes in the sizes that we can buy very cheaply today. So a quarter terabyte should not be considered a large number because it costs only $8,000. The fact that we think of it as large and scary is just a testament to how bad things are from a software behavior point of view. But we are in a world where a terabyte and 2 terabyte computers are very affordable today, and we have the real world problems, the in-memory business computing needs to fill them up. Solving the problems so that you can actually run on those well is important. And then having a young generation, a young generation that's not stopped the world is also important. The only reason that the young gen pauses are not a big problem today for most applications is that heaps are tiny and young gens are tiny. If we had a 100 gigabyte heap, it would be very normal to see a 1 or 2 gigabyte promotion from the young generation in a single monolithic operation that would be deadly, which is why we don't do it. But if we had a concurrent young generation, then that problem would go away as well. So with that as background, we can look at the Azul C4 collector, which is actually designed to address all of those. Classification-wise, similar to how I classified the other collectors, the C4 collector has a concurrent guaranteed single pass marker. This is not a multi-pass marker, and it doesn't care about mutation rate. There is no need to track mutation in this collector because it is not sensitive to mutation in any way. What this means is that it can keep up with any mutation rate without losing concurrency and without having to fall back. It also has a concurrent compactor. It can move objects from one point to another without stopping the mutator. It can also remap the references, fix up the references to those objects without stopping the mutator. And the fact that it could do both of those operations while the mutator is running means we can do compaction, which is the hardest thing for collectors to deal with usually, concurrently with the application and not stopping it using the plenty of empty CPUs that are around in the memory and the memory bandwidth and letting the application run while we do. From a classification perspective, it's a concurrent compacting old generation and a concurrent compacting new generation. And most importantly, there is no stop the world fallback here. These are the only modes this collector supports. From an algorithm point of view, I'm not going to get too much into the details, but The collector actually uses exactly the same algorithm for both the old and the young generation. It's a mark compact collector. Um, the reason there's a young and old generation is because that is 20 times as efficient as a single generation mark compact for us. So we obviously like to gain the efficiency. That efficiency means higher throughput. It means we can keep up with 20 times the allocation rate as we would have if we didn't have a generational collector. But from a pause time perspective, both the old gen and the young gen have exactly the same characteristic, which is they stay concurrent, and therefore there is no larger pause or smaller pause in the old gen or young gen to trade off. It's only efficiency that matters there. It uses a new and presumably novel kind of read barrier. It's called the loaded value barrier. We know that it's new and different because if you look at classifications of read barriers, it doesn't fit any of the ones in the academic work. And there's new academic work on it that I mentioned earlier. And then it's got some other really cool mechanisms under the hood. Um, rather than go into the details there, I'm going to show some of the benefits. The actual benefit um, of the C4 collector is that it completely eliminates garbage collection as a concern for most enterprise applications. It doesn't take garbage collection away, it makes it a non-issue. It makes it something you don't spend much time thinking about anymore. And the way that works out is in a few different places. The first one is GC tuning. I mentioned before in response to some questions, tuning is something you should plan on spending a lot of time on in most JVMs. These are examples of actual tuning flags from actual JVMs for modestly sized applications in the 8 and 12 gigabyte heap size examples. And I think to understand here is there are a lot of flags. The flags have right values. The right values are different for different applications or different settings or maybe different days of the week. And every time you change your application and your load and your code or your users, you might need to retune it because when you have so many different right settings, you've arrived at those right settings through experimentation and the thing you're experimenting with is moving. Zing, in contrast to that, is focused on tuning without having to know all these flags and simply setting a large heap size. Usually the way we start off with Zing is you just set a very large heap size, much larger than you currently use. And we don't do that because we need more memory. We do it because there's no negative effect to using it. It's the fastest way to get to a working system, and we can come back to it and tune it later. Now, once you've established a good, happy working system, you can come back to this number and say, well, I don't need 40 gig. Let's see if 20 gig works. And if that works, let's see 10, maybe 5, maybe 2. You could keep squeezing this down until you reach a breaking point, which is one knob to twist. Twist it until it breaks. And once you've broken it, just twist it the other way, 3x, 4x the size, and you're done tuning. And that's the entire tuning exercise needed for that, which is why we say that it eliminates the GC issue completely. So for regular enterprise applications, that's all you would be doing. For low latency applications, there are 2 or 3 other flags people use, but literally the flags and the number of tuning knobs that are needed are dramatically lower. And the reason here is because most of those flags are there to help you try to control stop the world behavior. And since Zing is a concurrent compactor, there is no stop the world behavior needed to be tuned. And as a result, most of the motivation for all those flags is gone to begin with. Now, in real effects, what happens when you turn it on? This is actually a first day's run sample from an e-commerce application that was pausing for about a second and a half, a few times an hour, and that was well above its SLA for responsiveness because it's a payment system. This is the first run on it on Zing, and it's about a 10-hour run. And the top of this graph is about 5 milliseconds. That's every single pause experienced by the JVM. The biggest pauses here, by the way, are not garbage collection. They're related with other things like lock deflation. But they're all sub 10 milliseconds in size. And as you can see, it's a very busy system, but it no longer pauses. In a low latency environment, this is a trading system after some more significant tuning, a few days of experimentation. In a trading system, you usually see much lower loads, much lower allocation rates to begin with because they're very, very sensitive to latency. But here, the 1 millisecond line is about halfway up this graph. And as you can see, after some initial warm-up that hit a couple milliseconds of pauses and no more, things stayed to about a 1 millisecond level consistently over a long run. Now, beyond just latency, it's important to look at throughput. And throughput is not just a number you try to measure by seeing how fast you can go. You need to figure out how fast you can go while maintaining your requirements. In this picture, driving a red car into a pole and then seeing how fast you could do that is not a good metric of, how good the car is. The real question that should be asked is how fast you can drive this car without hitting the pole. And sustainable throughput is similar. It's how fast can I drive my system without breaking, without hitting and breaking through requirements. And this is really where the comparisons that we like to do shine. This is a good example of comparing a messaging system measured by how many concurrent users it could distribute measurements to, or messages to, and different loads and different systems. It's the same physical system, but different JVMs. This, by the way, is how I recommend people look at measuring and comparing latency curves across different setups, whether they're different throughputs, different loads, different systems, or different JVMs. What you're seeing here is the hotspot JVM running at multiple different loads, 15,000 user load, which it can carry, but fails miserably on service level requirements. And then at lowering the loads to 10K, 5K, and eventually 1K, you can see that the latency curves get better and better to the point where the latency curve actually fits below the requirements line at 1,000 users. So while the system can handle 15,000 users if you don't care about responsiveness, it only handles 1,000 users while meeting the requirements. At the bottom right, you can see the Zing results for all four speeds at 1K, 5K, 10K, and 15K users. There are actually 4 lines there, but they're kind of hard to distinguish because the responsiveness across the entire percentile curve is extremely good. And it's the GC pauses that were causing those breakage of SLAs that are gone and that allow us to carry this load. As a result, we're able to carry 15,000 users on the same physical system while maintaining requirements, while Hotspot can only carry 1/15 of that while maintaining requirements. If all we did is measure how fast both systems can run into a pole, we would have gotten the same number. But if we want to see how fast we could run without running into that pole, the difference is pretty strong. Now we can measure it with portals, and I'm not going to spend too much time on that, but JHiccup is a tool I mentioned already, and a fun way to use it for us is to compare things. This is a tweet by Charles Nutter. He's the JRuby guy that honestly describes what it is we built it for, or what my not so hidden reason for building it. It's a very useful tool for studying systems in general, but it gives us a great way to compare Zing and others. So you can compare Zing on the left with Hotspot on the right, and you can see that both of them are spiky. We're talking about very different scales. If I normalize it, Zing is pretty much quiet, and on the right you have big pauses. It's a very simple picture worth 1,000-word comparison of the before-after effect of using Zing. Similarly, if we look at low latency applications where tens of milliseconds are a terrible thing, and using a similar trick, we kind of look at both of these, but highlight the scale. They're very different scales, and normalized, they look like this. Zing is simply a dramatically better platform to run this application on if you care about that jitter and noise, and you want to get rid of it because it causes trade risk. And I'm going to pause here for a second, take a couple more questions, and then I'll be happy to give an overview of Zing if there's any time left.
Okay, we've got a couple of questions queued up. We're 5 minutes to the top of the hour as well, so I'm not quite sure if you
Yeah.
want to go for a couple of extra minutes, Gil, or if you want to start wrapping up, but we can take a couple of questions. So can you... Yeah, let me just go back to the questions, make sure I don't ask the same one again. One of the questions is, in Java 7, the default garbage collector is said to be better than the other collectors. Is this true?
In Java 7, the default collector is still parallel GC, which is the same as it's been for more than a decade. Um, I don't think much has changed in it. It's just that we've gotten, faster machines and better CPUs, so you can probably do with a 4 gig heap what you used to do with a 2 gig heap before for the same, pause time, but it hasn't dramatically changed in the default, no.
Okay. Can you explain what a memory leak is, and how does that relate to garbage collection?
So, a memory leak is basically a situation where as you run your application, the amount of stuff in the memory keeps growing for some reason, right? And that some reason is not intentional. It usually is associated with a bug in your application and your coding. And there are multiple reasons for memory leaks. Garbage collection systems like Java eliminate a significant set of classes of memory leaks, the kind where you allocated, but you forgot to free something, and that without the free being there, you start accumulating dead memory. It's very common in C and C++ applications, especially as complexity grows, and especially as data graphs grow. Um, in in garbage collected environments, entire classes are gone because the collector will find anything dead. You don't have to free it. But there's still the type of leak where you just keep accumulating things and you forget them. You don't have to free them, but if you are keeping them around, if you keep adding to what you have, it's not going to go away. So they're usually in production. Usually you see this by seeing a creeping increases to your live set, and then you try and figure out where it's coming from.
Okay. The related question then is, does the use of garbage collection guarantee that there are no memory leaks?
No, it does not. As I said, there are still classes of memory leaks. They're always going to be your fault because you're doing something wrong and keeping things around. But again, I'm talking from personal experience. I'd say about 80% of the types of memory leaks or the causes of memory leaks are gone in garbage collected systems. So, um, the common things you see often in non-garbage collected systems is a doubly linked list needs some special behavior in order to free in most systems. So you either avoid using it or you have somebody whose job it is to break it apart so it could get freed. In a garbage collection system, you don't even have to think about that kind of thing. So all the classes of bugs that come from not getting that right are gone. But the part of my stuff is still growing because I increase my session state all the time and I forgot to forget things. I forgot that this is temporary and I should just not have it around. Is still there, unfortunately.
Okay. So relating to when you're working with I/O resources, you mentioned earlier that there wasn't any benefit from setting references to null. So the question is, when you're working with I/O resources, is it sufficient just to close the resource, or do you still have to set the reference to null anyway?
So setting references to null in order to help things is never needed in any of the situations. Um, the example of if you're leaking by adding more and more things to an array and growing your collections, then at some point you know you don't want to be growing your collections. You need to discard them for some reason, but you should be thinking of that as removing things from collections, not setting things to null. Um, if you have a thing that points somewhere and there's one of that, um, you don't need to set it to null for that to die before you yourself die. If you're going to be gone, it's going to be gone too, unless somebody else needs it. So in general, anytime you feel an urge to set a reference to null to help something, think twice. But do remember that retaining for no reason is going to eventually leak. The thing is that you usually don't have to, in most ways of programming, you don't actually have to actively think of setting things to null. You just go out of scope and things go away.
So is there any benefit from setting things to null? Say if you're in some long-running method and you're iterating over something, should you just wait until you get to the end of the method and you exit and things get dereferenced by default, or is there any benefit from setting things to null?
Um, there are very few long-running methods that are running long enough for that to matter. You know, uh, that a long-running method where you're in a loop and you never come out, well, obviously anything you point to is alive. But that's usually one or two of those in the entire program. Um, but if you're, say, working on a transaction, it's very natural to keep whatever the transaction state is within your state, and when you're done, you're done. And you don't have to clear it early, or in clearing it, earlier in a method or in a loop is going to be microseconds of difference than when it gets freed. Garbage collection is usually, when it's healthily tuned, run on seconds of time. So things will die naturally.
Okay. So one more question. Can you talk about how the promotion process works when things get moved from the young generation to the old generation?
So this varies by collector. I'll talk about both Hotspot and Zing there. In Hotspot, it's counted by number of young gen cycles. So there's basically a threshold for how many young gen collections go by before you push this into the old gen. And there's a counter on each object that says how many times it survived. That counter is either set to a hard threshold, or the JVM often has a heuristic that tries to play with it. You can actually control it. So the first time around you found them alive, you say, okay, first time I've seen you, you count it once, you keep them in the young generation, you copy them in the young generation. You do it once and twice and three times. When he hits the 5, like, let's say, suppose the threshold is 5, then if you see an object whose count is 5, GC young count is 5, then you move it to all gen instead of keep copying in the young gen. That's how it works in most of the collectors out there. In Zing, we actually use a different criteria for promotion because we don't actually distinguish in between space in the young and the old gen. They're just a concept of time. We consider anything older than a certain amount of time to be old. And that time is settable, but in practice, none of our customers have ever needed to set it. Our default time is a second. If an object is older than a second, it's old, and if it's younger than a second, it's young. And all that determines is whether the concurrent young gen keeps it in the young gen or promotes it to the concurrent old gen. Since it's purely an efficiency choice, not a pause choice, people just haven't really found the need to tune it much.
Okay, great. Do you need a couple of minutes to wrap up? Do you have a few more slides to go through? There's one more question we could take, or we can do a wrap up.
Um, let's do the one last question, and then there's just 2 slides, so I'll do those and message. So let's take the
Okay.
last question.
All right, last question is, how does the garbage collector work with the permgen in the JVM?
That's a big one. So this depends on which JVM and which version of Java. Currently, the permgen is there in all hotspot versions, and the permgen was intended to be older than oldgen. It's where the classes and the things that are not supposed to be going away are. Unfortunately, Java loads and unloads classes in the normal course of things, so the permgen needs to be collected. It's badly named perm. Um, Usually a permgen collection is a full stop the world collection in most JVMs, and as a result, it's a painful thing to set and painful thing to manage. In Zing, the permgen is simply part of the oldgen. We do track from a stats perspective because people want to see its size and how many loaded classes affects its size and stuff like that, so we allow monitoring of it. But it's simply a part of the concurrent oldgen. It's a non-stop the world collection, just like everything else. In Java 8, as some of you might have heard, there's going to be a shift in permgen. In effect, permgen is eliminated. There's no longer going to be something called a permgen, and it's replaced by something else called a metaspace that is not on the heap. It's still garbage collected in a different way. It will still have different settings, but they're different from the historic ones that have been used. And that's yet a different approach. In Zing, our approach had been not to go that way because once we've made it pauseless, we don't care about it anymore, and we're fine with the permgen the way it is. In other JVMs where pauses on permgen are very painful, people are still doing things to incrementally reduce them and help manage them. So I'm not sure if we have a hard stop on this because we started a few minutes late. I have two more slides and then we'll wrap up. So I'm going to do a quick overview of Zing here because, we talked about garbage collection and some setup for this. Zing is very simple. It's a JVM for Linux x86. As I said, it eliminates garbage collection as a concern, and it works across an extremely wide operating range. So everything from low latency to large-scale enterprise applications, anything from a gigabyte of memory to 300 gigabytes of memory, and everything in between runs smoothly on it. And it basically achieves that decoupling of scale from response time. So it's not just for large things, it's for anything where you don't want response time to be a controlling factor anymore. Um, we basically apply it anywhere that there is Linux x86 and Java, and for any application larger than about 300 megabytes of memory, you will see better metrics for latency. Whether those better metrics are something you need or not depends on your requirements. But if you are struggling with responsiveness behavior, with outliers, with glitches, you're spending your time tuning this stuff, then Zing is probably in your wheelhouse on these systems. Where it really shines is all four of these. In low latency, we pretty much have no competition. So if you're in a trading system or in a low latency messaging system, the fact that GC has gone usually means that a third or half of the engineering effort goes away as well. In human response time applications, a lot of the annoyance goes away. In retail systems, people are happier. Online retail stores generate more revenue per visit, all that kind of stuff, simply because things run smoother, especially at peaks. And then we have the in-memory analytics part, which is becoming more and more popular, where you see applications with humans interacting with large analytics in-memory applications that are expected to be very interactive. They crunch tens of gigabytes of state to answer questions like risk or ad placement or business intelligence, and it's usually a data exploration exercise. Um, in those systems that work very well, and most of them tend to be working in Java, the annoying thing is the multi-minute pause that you would get on a regular JVM every once in a while, at least in the tens of seconds. And Zing just eliminates that and keeps people happy and lets them scale. So again, that's yet another area for us. And that's it. That wraps it up.